Now that we've talked about 2D equilibrium and 2D space, the next logical leap to take would be to start to work in three-dimensional space. Why? We live in a three-dimensional world. All the objects and everything in our world can be represented in 3D space. So this video is going to focus on how we can represent some of these vectors in 3D space and some formulations for some of these vectors. The first thing we need to do, we need to change our coordinate system, which in 2D space only had two axes, the x and the y, and we need to add in a third axis. And when we add that in, we're going to have this z-axis right here. Now, depending on the reference material you have, maybe x is over here, y is over here, z is over here. But it doesn't matter. All that matters is it follows what's known as the right-hand rule. With this right-hand rule, what we do is that's my hand, we put my hand and we point it along the x-axis. Then the next thing is we curl our fingers from x to y. So we curl our fingers in that direction. When we curl our fingers in that direction, there's only one way that our fingers are able to actually curl. So these are my knuckles, these are my fingers when they're curled into a fist. But what we want to do is we want to notice where my thumb points. My thumb is always going to point in the positive z direction. And that positive z direction is that positive z direction right there. So while the actual location of x and y and z might change based on the book you're using, they're all going to follow this right-handed coordinate system. So now that we have the x, we have the y, and we have the z, we're going to introduce a vector. And we're going to say this vector right here is, we'll call it some point p. And p is a vector that is in 3D space. So what that means is, I have to go so far along the x, the y, and the z direction in order to get to this point. So I need to go somewhere over here. I need to go somewhere over here if the y-axis extended a little bit further. So I'm in 3D space. I'm not along this plane right here. It's hard to draw, but I'm not just along that plane. So now this is some point P, and in space it has a point of x, y, z. I go so far this way, and so far up the z-axis. There's an alternative way I could write this, and we're going to start this way. We're going to say I can go along this vector, and we'll call this vector p prime, and then I can go up along the z-axis. So this right here will be vector pz. So my vector p, one way I can write this, these are all vectors, is equal to p prime plus pz. And that's just vector addition. Now, what is pz equal to? Well, I can go this way along the x. So this can be some px. And I can go this way along the y. And this can be py. So I have p prime, my vector, is equal to px plus py. Now I can substitute what this p prime is into this equation. So I get my vector p is equal to px plus py plus pz. So I'm going here, px, py, and pz. And I get to the point, my point p. Okay, now this is a vector formulation, and what we're going to do a lot, remember with 2D coordinates we used I and we used j components. So when we used I components, I always pointed along, it was a unit vector that pointed along the x-axis. So right here, this would be I. J was a unit vector that pointed along the y-axis. And we're going to introduce K, which is a unit vector that points along the z-axis. Now, a vector, just to refresh your memory, a vector needs a magnitude, which is how long it is, and a direction, which is the unit vector. So the magnitude of px is just this number of how long it is, px. So I can represent this a different way. I can say that this is going to be equal to my magnitude, which is px, in the I direction, plus my magnitude py in the j direction, plus my magnitude pz in the k direction. And this is probably one of the most common ways you'll see these vectors written, especially in statics. Now, one of the most important things that we're going to be interested in solving for is the resultant, or how long that resultant is, the magnitude of that resultant. If you remember, in 2D space, let's say I had a vector that had some length px. Let's call it a so we don't confuse ourselves. So this was some length ax, and this was some height ay. Then my resultant, a, would be the point from the tail to the tip of tail of ax to the tip of ay, and my magnitude of a would be equal to the square root of ax squared plus ay squared from the Pythagorean theorem, right? This is a right triangle. We are going to use the exact same concept to figure out the magnitude of the vector in 3D space. So let me get rid of these vectors right here. And the first thing I'm going to look at is I'm going to look at this in terms of p prime and pz. So if we think about looking at this straight on, this right here is a triangle. It's a triangle that has my right angle right there. So if I draw this, and this is my p prime, and this is my pz, this is my magnitude of, this is p. So the magnitude of p is just like it was in 2D. It's equal to the square root of p prime squared plus p, and let me put this in parentheses just so, p prime squared plus pz squared. Right, this is my right angle. Now, let's look at this a little bit more. Okay, what is p prime? Well, p prime is a magnitude, and p prime is a magnitude with a right triangle right here. So I have a right triangle that's right there. So I could draw this again. And when I draw this again, if I do it the right way, this is my px. This is my py. And this is p prime. So if we do the exact same thing, my magnitude of p prime is equal to the square root of p x squared plus py squared. And I can write this slightly different, right? Instead of saying this is the square root, I can square both sides. The square root now goes away, and I have, well, the magnitude. I'm going to get rid of these magnitude bars just for simplicity. And then I have p prime squared is equal to this px squared plus py squared. So I can substitute this into here, and I can get that the magnitude of P is going to be equal to the square root of Px squared plus Py squared plus Pz squared. So the magnitude of a vector is the sum of all the squares of its components. And we see that in this equation. On an exam, memorize that. Memorize that if I have a vector and I'm looking for the magnitude of it, it's going to be the sum of the squares of all the components. So there we go. That's how we figure out what the magnitude is. So now that we figured out what the magnitude is, we need to figure out the direction that this vector points. And in 2D space, it was rather easy, right? We had, okay, we're trying to figure out whatever this angle right here is for theta. And we knew that theta would be equal to the inverse tangent of Py over Px. And that would give us what our angle is. Now with 3D space, it's not as simple as that because it could be in between 3 different planes. So what we need to do is we need to identify 3 different angles that we're going to use. Now these angles, if this is x, I'm going to call, this is my cosine angle or my coordinate direction angles. And this angle is going to be called alpha between my positive axis y in my vector. This angle I'm going to call beta. And between my positive axis z in my angle, I'm going to call this angle gamma. Now these angles are always going to be between 0 and 180 degrees. And these angles are going to be able to identify this point in space. Now, what are the equations for these angles? Well, let's just write these equations down and verify one of them. So here I'm going to have the cosine of alpha is going to be equal to Px over P. And this is the magnitude of P. So I should say this is the magnitude. I'm going to have the cosine of beta is equal to Py over P. And I'm going to have the cosine of gamma is equal to Pz over P. And now let me get rid of this magnitude just so I have some space. And let us verify one of these. Now this is hard to verify because this point is in 3D space. It's not the way I drew it and the way it looks like it's in this YZ plane, which it's not. So I need to have this point. I'm going to verify the Y. But you have to imagine this triangle is a plane that is a right triangle. And this, I'm telling you, is a right triangle. So the plane is sort of tilted. So it goes from this y-axis and tilts in so it's touching along that P vector. So if I have this right here and I draw this so it's projected just in 2D, this is my y. So this right here would be Py. Now, this is another one that I know. It's my magnitude P. So this is my angle beta. I don't know what this height is. I just don't know what this is. This is a question mark. But I'm just trying to identify this equation right here. Now, if we look at SOHCAHTOA, and we look at what I have, this is my hypotenuse. This right here is my adjacent. So this right here is my angle. So I know that the cosine of beta is equal to the adjacent, which is py, over p, which is the magnitude. And that's exactly what I have right here. And that same thing is going to happen for the cosine of alpha and the cosine of gamma. If you take the time to try to draw this in 2D, you can see that all of these, this is where this equation comes from. What we can now do is we can use what we have on the screen to sort of come up with a couple of different forms we'll be able to use for these problems. So a very common thing is we want to express this vector in terms of the unit vector and the magnitude. So if I have this vector p right here, p, this vector, is equal to whatever this magnitude is, so however long it is, so that's the length, times this direction, and we're going to say this direction is a unit vector in the direction of whatever this vector is, this unit vector of p. So this unit vector points along the line, the vector p. So this is going to be equal to u p. Now we can solve this equation for the unit vector, and we can have that this unit vector is equal to my vector divided by the magnitude. Well, we have an expression for the magnitude, right? Right up here, that start equation I have that this is equal to pxi plus pyj plus pzk divided by p. And we can write this, just simplify it a little bit. We can say this is px over pi plus py over pj plus pz over pk. All right, so now let's look at this. This is equal to this. This is equal to this. This is equal to this. So I can rewrite this slightly different. Give myself a little bit of room. And I can say that this unit vector p is equal to the cosine of alpha I plus the cosine of beta j plus the cosine of gamma k. That's okay to write. Now, this relates those cosine angles to the direction of this unit vector. And what's actually really cool is if I square both sides. This is just a unit vector. It has 1 in the x, y, and z. So if I take the magnitude, not square, if I take the magnitude of this and this becomes a 1. This becomes the cosine squared alpha plus cosine squared beta plus cosine squared gamma. Right? It's just like what we said here. It's the sum of the squares of the components. The x component, y component, z component. This is important because this tells me if I know any two of these angles, I can figure out what the third angle is. So if I know alpha and I know beta, I can figure out what gamma is. I don't need to, I only need 2 angles to know all 3. Now finally, we can write one more alternative form with cosine angles and vectors. So if I have p, this vector p, and this is equal to the magnitude times my unit vector p. Now we see we have an alternate expression for this unit vector, right? We already have an expression for that. So this is going to be equal to P times the cosine of alpha I plus the cosine of beta j plus the cosine of gamma k. Now, what we're going to also do is we're going to substitute all of these expressions into for the cosine alpha, cosine beta, and cosine gamma. And when we do that, we're going to have this is equal to px over px I plus pyj plus pzk. And let's just verify one of these. Why did this p go away over here? Well, if I take this cosine alpha I, so let's just look at p times the cosine of alpha I, and I substitute in px over p, I'm going to have p times px over p times my unit vector I. These p's are going to cancel, and this is going to be equal to px I. So these are just different ways that we can express these vectors in terms of cosine angles and time in terms of magnitude to represent where that vector is in space. And that becomes important so we can completely identify where this vector is in space. If my videos in statics are helping you, please consider liking my video and subscribing to my channel by clicking the subscribe button above my head. Both of these things help bring visibility to my channel and help my videos become more discoverable to help more people. Now, if you're looking for additional topics in statics to study, the playlist of statics is to my left, and hopefully you can find what you're looking for there.